Alright, this is our, I guess, fourth video in this case study. So, in the second video, we developed a model of the indoor air coils for a runaround loop. And then in the third video, we showed how to take those standalone models and turn them into procedures and integrate them with a system model. And this is the video where we'll actually develop the system model of the runaround loop. So here's the runaround loop. You can see it consists of two air coils, an indoor air coil that's energized on the air side by this indoor air fan, so it's blowing indoor air across that coil, and then an outdoor air coil over here where this outdoor air fan is pulling outdoor air across that coil to, in the winter at least, heat it up. And then these two are connected by an ethylene glycol loop that's energized by this gear pump. So this is a system, and anytime that you're simulating a system like this with some complexity, it's probably good to start out with some upfront thought about what your strategy is, and in particular sort of what are the inputs to the system, and then what are the things that you're going to want to change, and then most importantly, what are the variables in the system that have to internally be iterated on in order to make the system converge. So I've tried to do that here. I started with a set of inputs. These are things that I'm not going to change necessarily. I mean, I guess I can change them later on, but they'll be fixed as far as developing the system model is, and those are the geometry of the indoor and the outdoor air coil. So if I go back to where we left off last time, now I have this tab, which is the indoor air coil tab, and this is the geometry of that coil, its overall size and what the heat exchanger, compact heat exchanger geometry is. I'm not going to change that during the simulation. And then if I click on the outdoor air coil tab, I have the same thing. These might be different, but during the simulation at least they're going to be fixed parameters. So those are these first two things. The size and speed of these two fans are going to be fixed, so they're going to be flipped on, and they have a certain diameter and a certain speed, and I'm not going to change those. And then the size of the gear pump will be fixed, so that's basically the displacement of the gear pump. And then I'm just going to assume atmospheric pressure on the air side. The pressure will go up and down slightly as it goes across the fan and the coil, and then some nominal pressure on the glycol side. So let's go ahead and enter these inputs. So the geometry on the heat exchanger coils is already entered in their procedures, but I do have to enter the size and speed of the indoor blower. So let's do, I don't know, let's say the diameter is 12 centimeters and the speed is 20 revolutions per second. So that's the indoor blower, and the same thing for the outdoor blower, so there's probably no reason to make it different. We'll do 12 centimeters and 20 revs per second for that. And we need to enter the displacement of the pump. So I'll call that V displacement pump, and that's going to be 0.5 centimeters cubed. Let's convert that to base SI units. And while I'm thinking about units, let's go up here and put a dollar unit system directive. Alright, and then what else do I got to put here? I got to put some nominal pressure on the ethylene glycol side, so 1 atmosphere. And some nominal pressure on the air side, so that'll also be 1 atmosphere. So PA equals 1 atmosphere times. So those are my inputs. I'll go ahead and solve, and the units are all set here, so that's all good. The next thing I want to do is think about operating conditions. So these are things that I am going to change as I run my simulation. So the indoor air temperature may not change too much, but the outdoor air temperature certainly will. I can change the concentration of the ethylene glycol, and I can change the speed of the gear pump. I might change those two things to keep the glycol from freezing. So these are going to be in a different category, which I'll call operating conditions. And let's see, so just making some numbers up here. I guess the indoor air temperature in Fahrenheit would be something like 70, and we'll convert that to Kelvin using the convert temp function. So from Fahrenheit to Kelvin, T indoor F. Same thing for the outdoor air temperature, except we're going to do this on a cold day. So the outdoor air temperature might be something like 20, and we'll probably play with that and make it colder sometimes. And then what else? I said that the pump speed is going to have to change, so let's set it for now to 20 revolutions per second. And the concentration of the ethylene glycol. For now we'll make it 28%. Oops. I'll get 20%. And we'll save that, run it. There's some unit error. These got to be in Kelvin. Like that. Alright, so those are the easy ones. The harder ones are the iteration parameters. So let's go back here and think about how I'm going to set my system up so that it converges. And there's a bunch of things that I'm going to have to initially guess and then eventually adjust the value of that variable so that the system is properly constrained. So let's start with the obvious one, which is the ethylene glycol temperature. So all three of these ethylene glycol temperatures are unknown, and eventually they're going to have to be figured out. And there's different ways to do this, but my strategy is going to be to start here at the T ethylene glycol 1 and guess some reasonable value for that. So you know it's got to be between the indoor and the outdoor air temperature. And then I'll run it through the indoor air coil, which will give me the ethylene glycol 2 temperature here. I'll run that through the pump, which will give me the ethylene glycol 3 temperature. And then I'll run that ethylene glycol through the outdoor air temperature, which will give me a new value for T ethylene glycol 1. And of course, unless I'm a really good guesser, that new value is going to be different than my guessed value, and that is how I'm going to figure out what the actual value of T ethylene glycol 1 is. So I need to both know the iteration variable, which is T ethylene glycol 1, and then also have a strategy for closing it, right? And you can see I'm going to close it by setting the outlet temperature of the outdoor air coil to the inlet temperature of the indoor air coil. And that's not the only one, right? The other things I don't know but need to figure out are the volumetric flow rates, the flow rates of the air on both the indoor and outdoor sides, and then the flow rate of the ethylene glycol. So the flow rate of the ethylene glycol, I can guess what that is. I can make a guess. You know, there's some limits that make sense. It's got to be between 0 and the displacement rate of the pump. But then I would vary that guess until the pressure rise produced by the gear pump is exactly equal to the pressure drop through the ethylene glycol sides of these two air coils. So that's how I'll close that up. And then on the air sides, so the indoor air coil flow rate, that's something else I don't know. And so I'll make a guess for that. And the way I'll close up that guess is I'll adjust the volumetric flow rate until the pressure rise across the indoor fan is exactly equal to the pressure drop across the air side of the indoor air coil. And the same thing down here for the outdoor air, right? The pressure rise across the outdoor air fan has to be balanced by the pressure drop across the outdoor air coil. So there's 4 variables here that I don't know, and I'm going to start my simulation by just setting them to some reasonable values and then going through the calculations. And then at the very end, there's kind of an art to actually figuring out how we close these up in a way that allows convergence. So let's start by just setting these to some reasonable values. So these are my iteration variables. There's 4 of them, right? I said that the first one is the T ethylene glycol 1, and a reasonable value for that would be T indoor plus T outdoor divided by 2. So I'm just setting this to the average of those 2 temperatures. That seems reasonable. I would do the volumetric flow rate of the ethylene glycol. I'm going to set this to some number that's reasonable. So this is .0001 meters cubed per second, which if you look at what that is in, let's do cc's per second, so centimeters cubed per second. That's a reasonable number given the displacement rate of the pump. There's another unit error, I might as well fix that right away. What else? I have the volumetric flow rate on the two air sides. So V dot A IC, and this is going to be initially 0.06 meters cubed per second, and then same thing here. V dot A OC is 0.06 meters cubed per second. So these are all set now, and the next thing to do is start moving through the simulation, knowing that at this point the simulation is going to be wrong because these are all set to values that are just kind of guesses, or good guesses, but they're just guesses. And then once I'm done with the simulation, I'll go back and close up each one of these 4 iteration variables using the strategy that I just got done describing. So let's go ahead then and start with the indoor air coil fan. So I'm going to get this from the component library. So if I go to function information and I select component library, first of all it's going to say you have to load that library. So I'm going to click yes and go ahead and do that. And you can see it puts up here the load component library directive. And then if I go through here, I want to look for fans and blowers. And there's a few different choices, but the most appropriate choice for this is probably a fan. And I can look at the information if I want, or even view the code, but I'm just going to paste this in there. Pasted it up here. I don't really want it up here. I want it down here. And you can see that the fan requires the fluid, which for us is just air. It requires the mass flow rate, which I have to calculate from the volumetric flow rate. So let's call this m dot a indoor air coil, and that's just the volumetric flow rate. I'm going to be a little careful. A IC times the density of air at the indoor air temperature and my nominal air pressure. P equals PA. Alright, so that's the mass flow rate of air going through the indoor air coil. This is T indoor. This is my PA. This is the speed of my indoor air coil fan, so IC B, and this is the diameter, ICB. And what this is going to give me is P out of ICB. If I'm interested, I can figure out the fan flow rate. So this is W dot, let's call it ICB. This is the air temperature coming out. So this is also the inlet temperature to the indoor air coil. So I'll call it T in. And I'm not sure I care much about the efficiency here. So this should solve, if I solve. Yeah. So now let's calculate delta P ICB. And that's just going to be equal to P out ICB minus the nominal pressure. And if I solve for that, I find out that this is negative, which just means that I've exceeded the maximum flow that this fan can give me, which is fine. My guess is too high, so I'll go back and change that guess here in a second. Let's get all my units squared away. There, so that's a positive pressure rise, and you can see now I'm getting positive powers and things like that. So that's the first component. The next thing I got to do is force the air through the indoor air coil. So that's going to go use this procedure that I wrote in the previous video. So we'll call the indoor air coil. It's going to take in the ethylene glycol temperature, which we said is TEG1. It's going to take in the air temperature, which for us is T in IC. Volumetric flow rate on both sides. This is V dot AIC. Concentration, which I have, and it's going to give me back the outlet temperature, which is TAG2, and the outlet temperature on the air side, which I'm going to call TOUT IC. This is what I'm dumping out into the atmosphere. This is Q dot in the indoor air coil, and the effectiveness, if I'm interested in that, which maybe I'm not. So let's go ahead and call that. And yeah, here this is negative because it's going, in this case, from the air to the ethylene glycol. Okay, so I think that is working now. So maybe the next thing to do is go through the gear pump. So we'll call one of the component library gear pump procedure. So here, component library again, pumps. There's two gear pumps. One lets you put in actual performance data for a gear pump that you know the model for. The other is more generic, where you can either put in these performance parameters or just use sort of reasonable values. So I'm going to use this one. And if you read the information, it'll tell you that if you don't want to specify these parameters, you just put in negative numbers. So call gear pump. This is ethylene glycol. This is the concentration of the ethylene glycol. This inlet temperature is TEG2. This inlet pressure is just my nominal ethylene glycol pressure. This is the speed of that pump, and then this is the displacement of the pump. And the mass flow rate of ethylene glycol I need to calculate. So this is m dot ethylene glycol is v dot ethylene glycol times the density of ethylene glycol at T equals T Eg2 and C equals concentration of ethylene glycol. And then these are just going to be set to negative numbers, -1. This one actually has some units, so -1 watt seconds per meters cubed, I think is the right units for that, and -1. And it's going to return the pressure drop, the pressure rise produced by the pump, the power required by the pump, and then if I cared, it would also give me the pump efficiency and the volumetric efficiency, but I'm not sure I care about those things, so I'll not return them. And hopefully this will solve. I have the same problem there with my guess. This is watts. You see this is negative, which means I'm a little too high on my guess value for the flow rate. I could reduce that just a little bit, maybe like that, and I think I'll be positive now, very positive, probably too positive. All right, so that's the gear pump. I need to calculate the temperature coming out of that gear pump. So there's different ways to do that. For now, I'm just going to ignore that temperature rise and say that the temperature coming out of the gear pump is the same as the temperature going into the gear pump. So TEG3 is TEG2. Then finally, I got to go through the outdoor air coil. So go to this tab, call this procedure here, go back, and we're going to call, this is TEG3, this is the outdoor air temperature, right? T outdoor. This is the volumetric flow rate of the ethylene glycol. This is the outdoor air flow concentration, and this is going to give me back TEG1. Of course, I already guessed TEG1, so let's call this TEG1 calculated. And this is then the outlet temperature on the air side, so TA out OC. This is Q dot OC, and if I cared, I'd also get the effectiveness, which I don't think I do. So let's go ahead and calculate that. Make sure it works, and it does. Set all the units. This is Kelvin, and I think this is in watts, and there's no unit problems. I should really be saving this as I go. And I think the last thing I have to do here is the outdoor fan, right? So this is the fan that's energizing the outdoor air coil. So yeah, let's go ahead and do that. So options, I'm going to call that fan component again. So I think that's fan 1. We'll paste it right here. This is air. This is the mass flow rate of the outdoor air. So this is m dot AOC is v dot AOC times density of air at T equals T outdoor, and P equals PA. This is m dot AOC. This is the outdoor air temperature, I think. This is my nominal air pressure. This is what did I call this? NOCB and DOCB. And then this is the pressure coming out of the outdoor air fan and the fan work transfer. And then finally T, I don't know what you want to call this. We'll call this TNOC because it's the inlet temperature for the outdoor air coil. So this actually right here, I got this wrong. This should be TNOC. Not that it matters much. And then the efficiency. And yeah, the delta P produced by the outdoor air coil is just P out OCB minus PA. And hopefully that all solves. And go ahead and go through the exercise of setting all these units. I have a pressure, I have a mass flow rate, and I think that's good. So now my simulation is complete but not closed off, if you want to think about it like that. So these pressure rises are not matching up with the pressure drops, and this calculated ethylene glycol exit temperature, right, not sure where it is, right here I guess, is not matching up with my guess. So all these guesses need to go away sort of one at a time, and that's our next thing we got to do.